Hello everyone, and welcome to our next video dealing with limits. This video does cover techniques for finding limits. So our skill objectives for this video are number one, find limits of functions using limit laws. Number two, find limits of functions using direct substitution. Number three, find limits of functions using algebra. And the last one, finding left-hand and right-hand limits to find a limit of a function. Use left-hand and right-hand limits to find the limit of a function. The conceptual objectives in this case are understand when limit laws can and cannot be applied. The first thing we want to do is look at the limit laws themselves, and there are a number of them. You'll see on this slide 5, and then there's some other ones on the next slide. What we have to do here is first we're going to let A and C be two real numbers. A is the value that x is going to approach, and C is just a general constant. And we're going to let f and g be two functions such that the limit as x approaches a of f of x is equal to the number L, whatever L happens to be. And the limit as x approaches a of g of x is equal to m. And with that, we're going to start out by looking at limit laws involving the five operations. Sum, difference, a constant multiple, a product, and a quotient. Now, the one thing you have to keep in mind here, I think as you look at these, the laws themselves make sense. They will, as you look at them, you're going to say, well, that's obvious. That's what it should be because, hey, we're adding two functions. This is what the limit would be. When we have the difference of two functions, this is what the limit of that difference would be, and so forth. So let's start out with the sum. The sum is, we're going to take the limit as x approaches a of f of x plus g of x. Well, that's going to equal the limit as x approaches a of f of x plus the limit as x approaches a of g of x, which we happen to know what those limits are. That's just going to be L plus m. So therefore, if I take the limit as x approaches a of f of x plus g of x, it's just going to be the sum of the two limits of the two individual functions. With the difference, it makes sense that would be the same thing. The limit as x approaches a of f of x minus g of x is going to equal the limit as x approaches a of f of x minus the limit as x approaches a of g of x, and that's going to be L minus m. Now with the constant multiple, that's where we're taking some constant times a function. So we're going to use, that's where the C comes in that we talked about up there. So the limit as x approaches a of a constant C times f of x is just going to be equal to the constant times the limit as x approaches a of f of x, which that is just going to come out to be C times L. When I'm dealing with the product of two functions, the limit as x approaches a of f of x times g of x is just going to equal the limit as x approaches a of f of x times the limit as x approaches a of g of x, which is going to be L times m. And the quotient where we're dividing is that the limit as x approaches a of f of x over g of x is going to equal the limit as x approaches a of f of x over the limit as x approaches a of g of x, which is L over m. And in this case, that's provided that m does not equal 0. So again, what you have in each one of these cases. In the first one, we know that the limit of a sum is equal to the sum of the limits. The limit of a difference is the difference between the limits. The limit of a constant times a function is the constant times the limit. And the limit of the product of two functions is the product of the limits. And the last one, the limit of the quotient of two functions is the quotient of the limits themselves, again, providing that the denominator does not equal 0. Now these limits, if it's hard to read, it might be hard to read my writing on this because it's small and it's a little bit smaller. If you want to take a look on page 1091 of your book, you will also find all of these limit properties there. Now this is just the start of them. We have a few more to do. Let's continue with them. Another one we did the first 5 over there. A sixth one deals with the power. And basically a power function. So what that means is we're going to take a function raised to a power. So the limit as x approaches a of a function f of x raised to the n power is going to be when I take the limit as x approaches a of that whole limit raised to the n. So I'm going to get L raised to the n power. And then if I take the limit as x approaches a of the nth root of f of x, that's going to equal the nth root of the limit as x approaches a of f of x, which is going to be the nth root of L. Now we do have some special limits as well, and all of these limit laws here can be found on page 1092 of your book. The first one is the limit of a constant. In other words, if I take the limit as x approaches a of some constant c, well, that's just going to equal c. Again, we don't have an x to plug anything in, so we're just going to get that out. The limit of the identity function, in other words, the identity function is y equals x. The limit as x approaches a of x, well, that's going to be a. The limit of a power function, where we have x to the n, the limit as x approaches a of x to the n is a to the n. And the radical function, the limit as x approaches a of the nth root of x, is going to be the nth root of a. And again, as with the previous five, I'm hoping that as you look at those five, these two up here and these four here, that you feel that they are fairly obvious, that they do make sense, because it would seem that would be a very logical thing to have happen with those. And these limit properties here will now be a basis for everything that is going to come from now on in terms of evaluating these limits. So the first thing we want to do is move on to some examples where we're going to use these limit laws to evaluate some limits. Now in this case, what I have is this diagram up here. And I want to go through on this one. We're going to be looking at the limit as x approaches 2 of 4 times f of x plus 5 times g of x. And then the limit as x approaches 2 of f of x squared minus f of x times g of x. Well, what we have to do on this is we have to look and determine what the limit is as x approaches 2. So I'm hoping that as you look at this, you say, oh, here's 2. So f of x, while we do have a whole, we can see as I come from the left and from the right, that my function values are getting closer to 6, so I can say that the limit as x approaches 2 of f of x is equal to 6. Same thing is true with g of x. While we do have a whole here at 2, I know as I come from the left and from the right, my function values are approaching this same location, which happens to be at -2. So I would say that the limit as x approaches 2 of g of x is equal to -2. So now to evaluate each one of these limits, I'm going to use the limit properties. And the first thing is on this, I know that the limit of a sum, where I have in this first one here, I have the sum of two things. The limit of that sum is going to equal the sum of the limit. So that's going to be the limit as x approaches 2 of 4 times f of x plus the limit as x approaches 2 of 5 times g of x. And that, by the constant multiple rule, is going to equal 4 times the limit as x approaches 2 of f of x plus 5 times the limit as x approaches 2 of g of x. And now using those properties, I know the limit as x approaches 2 of f of x is 6, and the limit as x approaches 2 of g of x happens to be -2. And so in this case, this is going to equal 4 times 6 plus 5 times -2, which will come out to be 14. So therefore, I would say that the limit as x approaches 2 of 4 times f of x plus 5 times g of x is going to be 14. Now let's take a look at our second one. In this case, we have the limit as x approaches 2 of f of x squared minus f of x times g of x. Well, again, by those limit properties that we had, I know this is going to equal the limit as x approaches 2 of f of x squared minus the limit as x approaches 2 of f of x times g of x. Well, in this case, again, by our limit properties, we have here in this one, we have the first term here, we have a power. So I know that's going to be the limit as x approaches 2 of f of x, that thing squared, minus the limit as x approaches 2 of f of x times the limit as x approaches 2 of g of x. And so in this case, I know that that is going to equal 6. The limit as x approaches 2 of f of x is 6, so that's going to be 6 squared minus 6 times a negative 2. So that will be 36 plus 12. It's plus 12, which will be 48. And so in this case, I can say the limit as x approaches 2 of f of x squared minus f of x times g of x is going to equal 48. At this point, if you're not sure about some of the calculations or how I work through these problems, you can take a look at some of the examples on page 1093 of the textbook, or be sure to pause this video here, look over what I did there, and make sure you're comfortable with that again. And if you're not, make sure to ask questions at our next class. Take a look at the next one. Now, in this case, this is where we're going to be using our limit, the other special limit properties. So in this case, I'm taking the limit as x approaches negative 3 of, and we'll just put in parentheses here, x squared minus 5x plus 10. Well, by our first and second limit properties that we saw in the previous part, that's going to equal, where we have the sum and difference, that's going to equal the limit as x approaches negative 3 of x squared minus the limit as x approaches negative 3 of 5x plus the limit as x approaches negative 3 of 10. Now what we have at each one of these now, well, we have a constant multiple here. And so I can say that's equal to the limit as x approaches negative 3 of x squared minus 5 times the limit as x approaches negative 3 of x plus the limit as x approaches negative 3 of 10. Now this is where we use our 4 special ones that we saw after we did our first 7 limit laws. In this case, we know that the limit as x approaches negative 3 of x squared is going to be negative 3 squared. And then minus 5 times the limit as x approaches negative 3 is going to be minus 5 times negative 3. Plus the limit as x approaches negative 3 of a constant, in this case 10, is just the constant itself, so I get 10. And so I now have negative 3 squared minus 5 times negative 3 plus 10, which gives me 9 plus 15 plus 10, which equals 34. So in this case, what we have is the limit as x approaches negative 3 of this polynomial here is going to equal 34. Now, you might be looking at this saying, wait a second, basically what we did here to find this limit is we just plugged in the negative 3 in for x. And that is true. And so one of the ways that you're going to use, one of the techniques you're going to use to evaluate a limit is going to be direct substitution. But there's only certain times that you can do that. And so what we're going to do on this, we'll move forward here, looking at with limits with direct substitution. For our purposes right now, we're going to be looking at direct substitution when we're working with a polynomial or with a rational function. Okay, there are other situations where we can do that as well, but in fact, a lot of times we can do that. But for our purposes right now, we're just going to start out working with these ones, with these two. So if we have a polynomial, the limit as x approaches a of f of x is just going to equal f of a. In other words, what happens when I put a, the value, whatever a is, in for x? With a rational function where f of x is equal to a numerator polynomial over a denominator polynomial, the limit as x approaches a of f of x is going to be f of a, which will be the numerator polynomial evaluated at a over the denominator polynomial evaluated at a, provided again that that denominator does not equal 0. For example, let's take a look here at what we have on these ones. The first one, we have the limit as x approaches 3 of x squared minus 4x. Well, what this tells me is that this is just going to be, I just put the 3 in for x, I get 3 squared minus 4 times 3, which will be 9 minus 12, which equals negative 3. So in this case, the limit as x approaches 3 of x squared minus 4x is equal to negative 3. In the next one, the limit as x approaches negative 2 of 4 minus 3x over x plus 7. Well, that's just going to end up being 4 minus 3 times negative 2 over negative 2 plus 7, which will come out to be 10 over 5, which will equal 2. So in this case, the limit as x approaches negative 2 of this rational function, that will equal 2. Remember, that's 4 minus 3 times negative 2 is going to make it a plus 6. So that's 4 plus 6, that's where we get the 10. And negative 2 plus 7 is where we get the 5. Now, there are times when we go through and do the substitution where things happen that indicate to us that really we can't use the substitution. We have to do something more than that. Substitution is still going to come into play, but we're going to have to do some algebra techniques to help ourselves out. So what I'd like you to do right now is pause the video, and I want you to find each one of these limits by using direct substitution and seeing what problem does occur. Welcome back. And when you did the direct substitution, what you should have noticed that in each case you would get 0 over 0. Now we know that we can't divide by 0, so you might be tempted to say, well, this limit then is undefined. But in reality, we have a different term for it. What we have is what's called an indeterminate form. In other words, 0 over 0 is it's different. It's a different type of undefined statement than what you have when you take 1 divided by 0. So in this case, when you get 0 over 0, what really that does is that indicates that there is a common factor. And so our job is going to be to eliminate that common factor. So in that first problem that we have up here, we got the limit as x approaches 2 of x squared minus 5x plus 6 over x squared minus x minus 2. Well, factoring that numerator and denominator, that's just going to be then the limit as x approaches 2 of x minus 2 times x minus 3 over x plus 1 times x minus 2. And so in this case now, at this point, we're able to go and say, well, there's a common factor, so we can eliminate that common factor. And so we now know that this is just going to be the limit as x approaches 2 of x minus 3 over x plus 1. And now I do the direct substitution. When I put the 2 in for x, in the numerator I'll get negative 1. In the denominator I'll get 3. So the limit in this case as x approaches 2 of x squared minus 5x plus 6 over x squared minus x minus 2, that limit comes out to equal the negative 1/3. Now let's take a look at the second one. Now the issue you have with the second one is that we have a square root that is causing us a problem. And what happens on this one? We are going to go through with this particular one, and we need to go and eliminate that square root. We're going to go and multiply the top and bottom by something so that I get rid of the square root in this problem. And so what we do, if you remember back to earlier in the year, we're going to multiply top and bottom by the conjugate of that numerator. So we're going to multiply that by the square root of x squared plus 9 plus 3. And so that's going to equal the limit as x approaches 0 of the square root of x squared plus 9 minus 3, that times the square root of x squared plus 9 plus 3 all over x squared times the square root of x squared plus 9 plus 3. Now, why do we do that? Well, what we have at this point now, you should recognize this, is we're multiplying these two together, and we're going to get what is really a difference of two squares. We have something in the form of a minus b times a plus b, and that we know is going to be a squared minus b squared. So when I multiply this out, what I'm going to get now is the limit as x approaches 0 of x squared plus 9 minus the second thing squared, 3 squared, so that's going to be minus 9 all over x squared times the square root of x squared plus 9 plus 3. So at this point here, I know that the 9's drop off. And so what I have at that point, this is equal to now the limit as x approaches 0 of x squared over the x squared times the square root of x squared plus 9 plus 3. Now the x squareds drop off, and so we really have the limit as x approaches 0 of 1 over the square root of x squared plus 9 plus 3. And that, as x goes to 0, the square root of x squared plus 9 is going to be the square root of 9, which will be 3. So that result is going to be 1 over 6. And so for this particular problem, the limit as x approaches 0 of the square root of x squared plus 9 minus 3 over x squared does come out to be 1/6. Our next example, though, is going to be one of the more important examples that you're going to be working with. It is going to it should look very, very familiar because you dealt with something very similar to this at the beginning of the year when we dealt with what was called the difference quotient. And so with that, we'll move to part. We have our limit by simplifying. And again, this is algebraic. And so what happens on this one? We're going to be given a function. In this case, I'm told f of x is x squared plus x. And I want to find the limit as h approaches 0 of f of x plus h minus f of x over h. You should remember this as being the difference quotient. So the two things I have to find f of x plus h, and I have to find f of x. Well, I already know f of x. It's right here. So what I have to do now is find f of x plus h. So f of x plus h. Remember, when you're evaluating this, whatever's here is going in for the variable. So that's going to be x plus h squared plus x plus h. So x squared plus x. So that's going to be x plus h squared plus the x plus h. Now we do have to FOIL that out. So when I FOIL that out, that will be x squared plus 2xh plus h squared plus x plus h. And I'll combine the like terms if I can. In this case, I can't. So I know f of x plus h is going to be x squared plus 2xh plus h squared plus x plus h. And so now I know what this piece is. I know what that is. I can now start going through, plugging everything in, and then simplifying it so I can find this limit. So I have the limit as h approaches 0 of f of x plus h minus f of x over h. That's going to equal the limit as h approaches 0 of the f of x plus h that we found here minus f of x, which we know of as x squared plus x. And so I do just distribute that negative sign in there. So this is going to equal the limit as h approaches 0 of x squared plus 2xh plus h squared plus x plus h minus x squared minus x over h. Now at this point again, I can combine the like terms. You'll notice the x squareds cancel out and the x's drop off. And so what I now have is the limit as h approaches 0 of 2xh plus h squared plus h over h. And now we need to reduce this fraction. And the only way we can reduce it is by eliminating a common factor. So the first thing I have to do is notice that h is a common factor here. So I'm going to pull out a factor of h. So now this part right here will become the limit as h approaches 0 of my common factor h times 2x plus h plus 1. What do I multiply h by to get this? 2x. What do I multiply h by to get h squared? It's h. And what do I have to multiply h by to get h? We get the 1. So I get h, when I pull that common factor out, I get h times 2x plus h plus 1. Now, and that's over h. Now at this point, now the h's drop off here. So this now has become just the limit as h approaches 0 of 2x plus h plus 1. Well, as h goes to 0, that term is going to drop off. And so my final answer in this case is 2x plus 1. This right here is the most important thing that we have done so far. This is the basis for one branch of calculus. We talked about that at the beginning of the year. I told you it was one of the most important things that we were going to do all year. It leads to this. What we're doing right now is doing the difference quotient and taking that final step, the limit of that, to get this piece right there, which is the 2x plus 1. Again, pause the video here. Make sure you are totally comfortable with everything I did in this problem, from here to how I plugged everything in to how I simplified it until I got my final answer. If you have questions, make sure you note those and be sure to ask them in our next class. The final thing we have in this video is finding limits using the left hand and right hand limits. So in this case, what we have we're working with, you've dealt with this with graphs, we're going to be looking at now as a piecewise function. So I have a piecewise function, f of x is in 3 pieces. It's x minus 3 when x is less than or equal to 1. It's equal to 3x squared minus 5 when x is between 1 and 2. And it's 4x minus 3 when x is greater than or equal to 2. Now, what we have on this one in terms of limits and working with this, we're really finding a limit on this one. There's only 2 places that I would have to have any concern. And that happens to be at where I have the endpoints of these intervals. So at 1 and 2 are the only places where I'm going to have a concern about the limit if the limit as x approaches any number exists. And the only place that it could be an issue is at 1 or 2, because that's where we break pieces here. And if I looked at this as if I was asking you to find the limit as x approaches negative 1, that would be very easy. If it's negative 1, it's going to be in this one right there. The limit as x approaches negative 1 of f of x is just going to be what I get when I put negative 1 into the function. So I'm going to get negative 4. The same thing with if I did something like f of as x approaches 0. That's 0, or sorry, if as x approaches like, not 0, 0's up in that one. If as x approaches 3 over 2, 1 and 1.5, I would just put the 1.5 in for x. 3 times the 1.5 squared minus 5, the limit would be whatever I get. Same thing if I did want to find the limit as x approaches 5, I'd just plug it into that bottom piece. But really what happens where we're concerned is, as at the breaks, do we approach the same value? So to do that, what I have to do is find the limit as x approaches 1 from the left and from the right of f of x, and I'll do the same thing for 2. Now, as long as when I come from the left and from the right, I get the same value, we know the limit exists. So let's take a look at the limit as x approaches 1 from the left. Because we're coming from numbers that are smaller than 1, I will use this top piece. So that's the limit as x approaches 1 from the left of f of x. It's just going to be the limit as x approaches 1 from the left of x minus 3. And I just plug in the 1. I get 1 minus 3. That equals negative 2. When I take the limit as x approaches 1 from the right, now we're putting in numbers that are slightly bigger than 1, but getting closer to it. That means it's going into that second piece. So that's going to equal the limit as x approaches 1 from the right of 3x squared minus 5. And again, by direct substitution, this comes out to be negative 2. Since both pieces are the same, I know that the limit as x approaches 1 exists, number 1, and that limit is negative 2. Let's take a look at what happens as x approaches 2. The limit as x approaches 2 from the left of f of x. Well, from the left, we're putting in numbers that are slightly smaller than 2. That means we're going to be putting it into this piece right here, that middle piece. So that's going to equal the limit as x approaches 2 from the left of 3x squared minus 5. And again, by direct substitution, that is going to come out to be 7. When I take the limit as x approaches 2 from the right, coming from the right, I'm putting numbers that are slightly bigger than 2. That means I'm going to be using this third piece. That's going to equal the limit as x approaches 2 from the right of 4x minus 3. And again, by direct substitution, I get 4 times 2 minus 3, which is 5. Well, in this case, The left-hand limit and the right-hand limit do not equal each other. So therefore, I would say the limit as x approaches 2 of f of x does not exist. With this, we now conclude the video dealing with the properties, using properties and algebra and some simplification to go and evaluate the limits. So make sure that you are comfortable with every calculation I've done in this video. Make sure that you note anything that you have questions about and make sure to ask them in our next class. So with that, I hope you are having a good evening and we will see you in our next class.